The structure and interpretation of computer programs, bite-sized. 1.2.3 Orders of Growth. The previous examples illustrate that processes can differ considerably in the rates at which they consume computational resources. One convenient way to describe this difference is to use the notion of order of growth to obtain a gross measure of the resources required by a process as the inputs become larger. Let n be a parameter that measures the size of the problem, and let R of n be the amount of resources the process requires for a problem of size n. In our previous examples, we took n to be the number for which a given function is to be computed, but there are other possibilities. For instance, if our goal is to compute an approximation to the square root of a number, we might take n to be the number of digits of accuracy required. For matrix multiplication, we might take n to be the number of rows in the matrices. In general, there are a number of properties of the problem with respect to which it will be desirable to analyze a given process. Similarly, R of n might measure the number of internal storage registers used, the number of elementary machine operations performed, and so on. In computers that do only a fixed number of operations at a time, the time required will be proportional to the number of elementary machine operations performed. We say that R of n has an order of growth theta of f of n, written R of n is equal to theta of f of n, pronounced theta of f of n, if there are positive constants k1 and k2 independent of n such that k1 times f of n is less than or equal to R of n, which is less than and equal to or equal to k2 times f of n. For any sufficiently large value of n. In other words, for large n, the value R of n is sandwiched between k1 f of n and k2 f of n. For instance, with the linear recursive process for computing factorial described in section 1.2.1, the number of steps grows proportionally to the input n. Thus, the steps required for this process grows as O of n. We also saw that the space required grows as theta of n. We also saw that the space required grows as theta of n. For the iterative factorial, the number of steps is still theta of n, but the space is theta of 1, that is constant. The true recursive Fibonacci computation requires theta of that symbol raised to n steps and space theta of n, where that symbol is the golden ratio described in section 1.2.2. Orders of growth provide only a crude description of the behavior of a process. For example, a process requiring n squared steps, and a process requiring 1000 times n squared steps, and a process requiring 3n squared plus 10n plus 17 steps all have theta of n squared order of growth. On the other hand, order of growth provides a useful indication of how we may expect the behavior of the process to change as we change the size of the problem. For a theta of n linear process, doubling the size will roughly double the amount of resources used. For an exponential process, each increment in problem size will multiply the resource utilization by a constant factor. In the remainder of section 1.2, we will examine two algorithms whose order of growth is logarithmic, so that doubling the problem size increases the resource requirement by a constant amount.